Year 12 Summer Assessment, Paper 2. We're going to work through each of the questions from the second paper of the summer assessment. So, question 1. The function f of x equals x squared plus 3 and g of x equals 2x. Find the composite function fg of x. So, we need to remember fg of x, of course, means g first, then f. So, it's f of g of x, which is f of 2x. Then I need to apply f, which tells me to square my input of 2x and then add 3, which gives me a final answer of 4x squared plus 3. Question 2 is really testing whether you understand the different aspects of sequences and arithmetic progressions. So let's break this down. The seventh term of an arithmetic progression is 6. So U7 is equal to 6. Now, the nth term, un, is equal to a plus n minus 1d. So this tells me that 6 is equal to a plus, and n is 7 in this context, so n minus 1 is 6, 6d. Now, we're then told the sum of the first 10 terms is 30. So we want this formula, Sn, the sum to n terms, which is equal to a half n 2a plus n minus 1d. So we know that S10 is equal to 30, the sum of the first 10 terms. So 30 is equal to a half multiplied by n, which is 10, 2a plus n minus 1, so that's 9 multiplied by d. And if I simplify this, this then gives me 6 is equal to 2a plus 9d. And I have a pair of simultaneous equations, and we're going to solve these. So 2a plus 9d equals 6, and then I'm going to write down 2 times equation 1, so double equation 1, which gives me 2a plus 12d equals 12, and then subtracting these will give me negative 3d equals negative 6, so d is equal to 2, and then I can substitute into any equation to work out my value of a, and it works out to be negative 6. Now the question actually wants us to find the fifth term of the progression, u5, which is equal to a plus 4d using this formula here. So that is negative 6 plus 4 multiplied by 2, which is 8, which gives us an answer of 2 for the fifth term. So question 3 is all about the modulus function, and we have y equals 2 multiplied by the mod of x minus 1. Let's have a look at the 2 points here. Now b is sometimes a little bit easier to calculate a y-intercept. So at point b, I suppose, x is equal to 0, so y is equal to 2 mod 0 minus 1, which is of course equal to 2. So that tells me straight away that b equals 2. Now we know at the x-intercept, y is equal to 0, which then tells me that 2 mod x minus 1 equals 0, mod x minus 1 is equal to 0, and it's clear from here x has got to equal 1 for this to work. So this gives me a equals 1. Now it's not specifically asking for the coordinates of these points, it's just asking for the numerical values here. Question 4, a first foray into some mechanics here. So we need to make sure we label a clear diagram drawing on the forces acting. So the 2.5 kilogram mass will have a weight of 2.5 g, and there will be a tension here like this. And the 4 kilogram block will have a weight of 4g like this and tension upwards like this. Now the blocks are held at rest, but then they are released. Now because 4 kilograms is heavier, the acceleration will start like that. It will move downwards, and the other block, the 2.5 kilogram block, will move upwards like this. Find the acceleration of the blocks and the tension in the string. So we are going to look at the two blocks separately, modelling them as particles. Let's start with the 4 kilogram block. I'm going to choose down as my positive direction. So I have 4g downwards minus t upwards like that, which equals the mass 4 multiplied by the acceleration. And I have a result here. Let's now look at the 2.5 kilogram block. I'm going to choose up as my positive direction. So this time I have t minus 2.5g equals 2.5 multiplied by the acceleration. And of course, in both cases, I'm making use of Newton's second law of motion, which tells us that the resultant force is equal to the mass multiplied by the acceleration. So in both cases, I've applied Newton's law of motion to the situation. Now, having set up these two equations of motion, we have a pair of simultaneous equations, and I'm going to add equation 1 and equation 2 because this very simply would cancel the tension here and here. And we then end up with 1.5g is equal to 6.5 multiplied by the acceleration. So this gives me a value for the acceleration, which is equal to 2.2615, so 2.26 meters seconds to the minus 2 meters per second squared to 3SF. But don't forget to store that in a calculator memory so you can use it then to calculate the value of the tension. So equation 2 tells me that tension equals 2.5g plus 2.5a, which equals 30.1538 ... So that's 30.2 newtons to 3 SF. Question 5. Solve the equation e to the 2x minus 5e to the x equals 0. Now, there are lots of different ways of solving this equation. What we are not going to do is add 5e to the x to one side and divide. We're going to think more carefully than that. And I'm going to factorise e to the x, which leaves me with e to the x minus 5 equals 0. Now, there are two things we want to consider here. Firstly, can we allow e to the x to equal 0? Unfortunately, we can't. There's no solution here, but we do need to actually state this and explain that there is no solution to this part of the equation here. Now, the second part, on the other hand, neatly gives us e to the x minus 5 equals 0, e to the x equals 5, and then x equals ln 5. You can write down a decimal value and round it, but as we haven't been asked for a rounded answer, I'm going to present my answer in exact form as ln 5. Now, a number of you do not always explain what happens to the other part of the equation. Sometimes in these sorts of equations you get two possibilities, both of which could work. Here, one possibility didn't work and you have to explain why. And the reason for this, think about the e to the x graph, it never crosses the x-axis. E to the x cannot equal 0. Question 6, some logarithms. Part 1, we have to express this as a multiple of log ax, or log to the base ax. So that means we need to write each part of this as a multiple of log x. So the first part of this is log to the base a of x to the 4, and we're going to pull that 4 out to the front using the log rule. So we've got 4 log to the base a of x. Now the second part of this is log to the base a of 1 over x, but what I'm going to do is I'm going to write 1 over x as x to the negative 1. Now I can then pull that negative 1 out to the front, so I get minus log to the base a of x using my logarithm rules. This then simplifies to give me 3 log to the base a of x, which is a multiple of log x. Now, part 2, we've got to find b in terms of c. Now, the first thing that we can do, which is quite nice here, and there are so many ways of approaching this question, so please don't think this is the only method here, it's just a possibility, is to combine the two parts on the left-hand side. So we can rewrite this as log to the base 10 of bc, which equals 3. Now, raise both sides so that we have 10 to the power on both sides. So on the left-hand side, this cancels the log to give us BC. On the right-hand side, we get 10 to the power 3. And this then allows us to write that B is equal to 1,000, which is 10 cubed, over C. Question 7, a little bit of kinematics here. A particle moves along the x-axis with velocity given by this result here. Find an expression for the acceleration. So what you need to remember, of course, is that the acceleration is the rate of change of the velocity with respect to time. It's dv by dt, which means it is 24 minus 12t. Part 2. Find the times at which the particle has 0 speed. Now, if a particle has 0 speed, that means v must equal 0, which means 24t minus 6t squared must equal 0. Let's divide through by 6. 4t minus t squared equals 0. Don't divide by t, factorise. You start to lose solutions when you divide through by a variable that could be equal to 0. Now, this then allows us to solve this quadratic equation, t equals 0 or t equals 4. So these are the times t1 and t2, so we could say that t1 is equal to 0 and t2 is equal to 4 seconds. Now, part 3, find the distance travelled between the two times. Now, we know that the connection is such that we can go from the displacement to the velocity to the acceleration by differentiating. If we want to go in the other direction, then of course we want to integrate. So to calculate the distance travelled, I need to integrate the velocity with respect to t between the two times 0 and 4. So I'm going to do this as a definite integral. So this is the integral of 24t minus 6t squared. Let's integrate between 0 and 4. So this gives me 12t squared minus 2t cubed. And we've got limits of 0 and 4. Let's input our limits, so 12 multiplied by 4 squared minus 2 multiplied by 4 cubed. And of course our lower limit will simply give me 0. So working this out then gives me a distance travelled of 64 metres. Now, if you are going to do this as an indefinite integral, you then have to include a constant plus c and then show that the constant is equal to 0 by saying that when t equals 0, the displacement or the distance travelled is 0, and then that allows you to work out the constant as 0. In many ways, it's easier to use the two limits and integrate between them. Question 8. We have some logarithms and exponentials here with some exponential growth. Question 8, part 1. Calculate the population when t equals 0. When t equals 0, p equals 10 minus 3 e to the 0. E to the 0 is 1, so this gives us a population of 7 million, not just 7. Now, there's another part to this, the long-term population. This is what happens when t approaches infinity. Now, when t approaches infinity, e to the minus t will approach 0. It doesn't matter that there's a factor of k there. As t gets larger and larger, e to the negative t will become closer and closer to 0. And you can check this on your calculator always. If you're never sure, input a very, very large value for t and see what happens. So this means that p will approach a value of 10 million. Now, part 2. The population when t equals 1 is estimated to be 8.6 million. We calculate the value of k. So 8.6 is equal to 10 minus 3e to the negative k as t equals 1. Let's rearrange this. So this gives me 3e to the negative k is equal to 1.4. E to the negative k is equal to 1.4 over 3. And then negative k is ln 1.4 over 3, which then allows us to work out the value of k, and this is 0.76214 ... so 0.762 to 3 significant figures. Question 9, some more kinematics. A toy car is moving along the straight line O to X. Now, when they say that, that means it's in the direction O to X, so towards the right. O is the origin. At time t equals 0, the car is at A, so X is equal to 3, positive 3, because it's on the right of the origin, and the velocity is given by this result over here. Now, calculate the distance of the car from 0 when its acceleration is 0. Calculate the distance of the car from O when its acceleration is 0. So we're trying to calculate the distance at a particular time. I don't know what that time is, but I know that we're looking at a time when the acceleration is 0. So I need to find the acceleration by differentiating. So I need to find A by finding dv by dt. Differentiating the velocity gives me 12 minus 6t. Now, when A is equal to 0, this tells me that 12 minus 6t equals 0, and this tells me that t is equal to 2 seconds. So this is the time in which we're working. Now, remember from a previous question as well that the distance travelled, so if we go from the distance to the velocity to the acceleration, we are differentiating, and if we want to go backwards, we are integrating. So I want to find x, which means I want to integrate 2 plus 12t minus 3t squared with respect to t, and this gives me 2t plus 6t squared minus t cubed plus c. Now, to work out the value of the constant, we know that at time t equals 0, the car is at A, 3 metres from the origin. We wrote down that information over here. So we know that 3 is equal to, well, t is 0, so these 3 terms containing t will cancel, leaving us with c equals 3, and we have a general expression for the distance, which is x equals 2t plus 6t squared minus t cubed plus 3, the displacement, sorry. Now, we're interested in what the distance travelled is at 2 seconds, so substitute in t equals 2, and let's see what we get. And we get an answer of 23 metres. Question 10, some functions work. So there's the line y equals x and parts of these curves here. So the curves intersect the axes at the points A and B. Let's investigate point A. So at point A, we're looking at y equals g of x, and we can say that y is equal to 0 for the function g of x. So g of x is equal to 0. So 1 plus ln of x equals 0, ln x equals minus 1. Now to undo this, we need e. So we need to take e to the ln x here, e to the negative 1. Of course, this cancels on the left-hand side, x equals e to the negative 1. So the exact coordinates of point A are e to the negative 1, comma 0. So that's point A. Now, at point B, we know that x is equal to 0 for the function f of x. So f of 0 is equal to e to the 0 minus 1, which is e to the negative 1. So the point B has got coordinates 0, e to the negative 1. Of course, a mirror image in the line y equals x of the coordinate A. Now, there's another part to this. Verify that the coordinates of C are 1, 1. So we could try and solve an equation by equating f of x and g of x, but you will find that's a very difficult, if not impossible, equation to actually solve. So a better way of doing this is to investigate each function separately. So at x equals 1, what does f of x equal? It equals e to the power of 1 minus 1, which is e to the 0, which is 1. And what does g of x equal? It equals 1 plus ln 1. Well, ln 1 is 0, so we also get 1. So we know that both f of x, y equals f of x, and y equals g of x pass through 1, 1. So C has coordinates 1, 1. Now, the last part of this, prove algebraically that g of x is the inverse of f of x. So let's start with y equals f of x. That's y equals e to the x minus 1. Now, I'm going to find the inverse function here, so let's rearrange. So x equals e to the y minus 1, swapping x and y. Now let's change the subject to the format y equals. So take ln of both sides. Ln x is equal to y minus 1. Y is equal to 1 plus ln x. Now that gives me f minus 1x, which is 1 plus ln x. And if you notice, that is the same as g of x. There are other ways in which we could have done this. This is just a very efficient way of finding the inverse of f of x. You could also have applied f and then g and then f to show that they cancel each other out and take you back to x. So there are multiple ways of doing this question. So question 11, we have quite a long mechanics question here. Forces, mass, acceleration, connected particles. Car of a mass 1,000 kilograms is travelling along a straight level road. Diagram needed. Here is the car. And here is its weight of 1,000 g. I'm going to draw the normal reaction force of the road pushing up on the car. And of course, the car must have a driving force like this, and there will be a resistance to motion like that, assuming the car is accelerating in this direction here. So, calculate the acceleration of the car when a resultant force of 2,000 newtons acts on it in the direction of motion. So part 1, we're using resultant force equals mass multiplied by acceleration. Now we're given the resultant force, so we don't have to worry about the separate forces acting, because we know the overall force is 2,000 newtons in the direction of motion. So that's 2,000 equals 1,000 A, so A is equal to 2 meters per second squared. Now, how long does it take the car to increase its speed from 5 meters per second to 12.5 meters per second? Now, part 2 relies on the assumption that the acceleration is constant. Now, if the resultant force is constant, the acceleration will be constant, which means we can use the constant acceleration equations, or as some people like to call them, the Suvat equations. Now, we don't know how far we're travelling. We do know that the initial speed is 5. The secondary speed, or the final speed, is 12.5. The acceleration is 2. And the time is what we are actually looking for. So if I take this out of the picture, let's use the equation v equals u plus at. And this tells me that 12.5 is equal to 5 plus 2t. And from here, it's very easy for us to work out that the value of the time is 3.75 seconds. Now, part 3, we have some new information to consider. The acceleration is 1.4 meters per second when there is a driving force of 2,000 newtons. So let's go back to this diagram here. Now, what we know here is now that the driving force, or the forwards force here, well, we can replace that with a value of 2,000 newtons. Let's do that first of all. We can also replace the acceleration with a value of 1.4 meters per second squared. Does appear to be a small typo in the question here. That should be an acceleration, so -2 there. And we've got to find the resistance of motion and show it 600 newtons. Newton's second law of motion, up here. I'm going to choose going to the right as positive. So we have 2,000 newtons minus F, there's the resultant force. 2,000 newtons in the positive direction, F in the negative direction, which equals the mass of 1,000 multiplied by the acceleration of 1.4. So 2,000 minus F equals 1,400. So it's very easy to see that F is equal to 600 newtons. Now, things change in this part of the question. a trailer is attached to the car as shown in the diagram. So the car still has a forwards driving force of 2,000 newtons. I'm going to redraw this diagram so we can see the model here, which is of connected particles. So here's the trailer on the left, the car on the right, and there's a tow bar, so a rigid rod that connects the two of them. Now, the car, we know, has a mass of 1000 g, and then there's a reaction force acting on the car. Now, the trailer, we're told, has a mass of 800 kilograms, so a weight of 800 g, and there's a reaction force RT acting on the trailer. Driving force, forwards direction, 2,000 newtons, and the car experiences, that's very specific, the car experiences a resistance of 600 newtons. Now, we need to include a tension force here and a tension force here in the tow bar, and we also need to include a resistance force here, which I'll call F, which acts on the trailer. Now, the system has an acceleration of 0.7 meters per second squared. Show that the resistance to motion of the trailer is 140 newtons. There are lots of different ways of doing these sorts of questions. This is how I like to do this. I like to look at the forces on each particle separately, starting with the car. Now, everything's going in a positive direction to the right, so that's my positive direction there. We're using Newton's second law of motion, again, F equals ma. So, for the car, we have 2,000 newtons forwards minus T minus 600 equals m, mass, multiplied by acceleration, 0.7. Trailer. Same idea, everything going to the right is positive, so we have T minus F equals 800 multiplied by 0.7. We have a pair of simultaneous equations, and I'm going to proceed to add them together because this cancels out T. So this gives me 2,000 minus F minus 600 is equal to 1,260. And we can rearrange this to get the value of F, which is the resistance to motion of the trailer, and that comes to 140 newtons as expected. Now, for part 4, to calculate the force in the tow bar, that's the value of T. So we take 140 newtons and then substitute it probably into equation 2 because that's quite a simple equation. And this then gives me an answer of T equals 700 newtons, so the tension in the tow bar is 700 newtons. Now, the system changes again. This requires us really to draw a new force diagram. So we have the car and we have the trailer. Let's put their weights in. And let's put in all the forces that we're not really that concerned about, the vertical forces here. There's the tow bar and tension in the tow bar here. Put in the forces like that. These forces, remember, are acting on the car and the trailer separately. The driving force is now removed and a braking force of 610 newtons is applied to the car. Now, a braking force is a type of force that will try and slow you down, so it will try and oppose the direction of motion. Remember, we're aiming to accelerate in this direction, so the braking force is in the opposite direction, 610 newtons. All the resistances to motion remain as before, so that means there's a resistance to motion of the trailer, which we worked out was 140 newtons, and we know that the resistance to motion of the car was 600 newtons. Running out of space really to put this. Hopefully you can all see my 600 newton resistance force. Remember, resistance forces oppose the direction of motion or the intended direction of motion, so they are both in these directions here. The trailer has got no brakes. Now, calculate the new acceleration. We're basically going to apply Newton's second law of motion again with this new system. starting with the car, everything going to the right is positive. So we have no forward force at all. We have minus 600, minus 610, minus t, which equals m, 1,000, multiplied by the acceleration, which is a value we do not know. The trailer, let's look at the trailer. We do have a forwards force. We've got t going to the right, but then we've got minus 140, and that equals its mass, 800, multiplied by its acceleration. Simultaneous equations again, and look at the plus and the minus t across the equations. Equation 1, add equation 2. What will that give us? It will give us a value of minus 1,350 on the left is equal to 1,800a on the right-hand side. So what does my acceleration equal? It equals negative 0.75 meters per second squared. So essentially there is a deceleration going on here, but it's fine to just write acceleration equals negative 0.75 meters per second. We're not asked for the magnitude, we're asked for the acceleration. Now, calculate the force in the tow bar. So in equation 2, I can see that T equals 800A plus 140. What does that give me? It gives me a value of, interestingly, negative 460 newtons. So what does this mean? This means that actually, if we look at the two objects, I've just worked out that the tension here acting on the car, let's highlight it slightly more clearly. I've worked out that this tension is negative 460 newtons, which means it can't be going to the right, which means the force on the trailer is 460 newtons like that. And there will be a matching force on the car of 460 newtons like this. Now, that means if we actually look at the tow bar itself, the forces in the tow bar must be equal and opposite to these two yellow forces. So there must be 460 newtons here in the tow bar and 460 newtons here in the tow bar as well. If we add the particles to this diagram, they would be here and here, the car and the trailer, and then we know there's 460 newtons like that now on the trailer, and there must be a matching 460 newtons like that on the car. Look at the two forces in the tow bar, these two. They are pushing inwards inside the tow bar. They are squashing the tow bar inwards, which means the tow bar is in compression, which is what we sometimes also called thrust.